So today we start a new lecture. We're going to talk about conversions, specifically conversions of mass to the number of molecules. In order to start the discussion, we first need to talk about Avogadro's number. This particular number, which depicts the total number of atoms or molecules that you may have present in a specific amount of bulk sample, has been determined via many different experiments. And the one that I'm going to show right here brings us back to the idea of the oil drop experiment of Millikan, where he has oil drop particles dispersed in these compartments. He lets them fall through, charges them up by using X-rays, and then uses positive and negative plates to um, basically suspend them in air. Ultimately, as you may recall from previous lectures, this allows to find out the charge of the electron. And a separate experiment, something that you'll in due time learn a lot about, is something known as electrochemistry, where you actually provide charge to a solution. So let's say that the solution that we have here contains copper 1. And what you do is you hook this up to a battery and you start transferring electrons into the battery itself. Now the electrode right here will be basically an electron source for which the copper can take up one of the electrons and become copper 0, or basically a solid. And the moment that happens, the copper starts depositing on the electrode. If you do this just enough so that you end up collecting 63.55 grams of copper, and you take care of the number of charges, the overall charge that is being delivered here, if you look at how much charge has been delivered, you're going to find out that upon collecting 63.55 grams of copper, you end up providing 96,485 coulombs worth of charge to the solution. And so what you can do is say, well, that's the total amount of charge, 96,485. And we know that for every electron that there is a total charge of 1.6 times 10 to the negative 19 coulombs. So that becomes a conversion factor. And what this basically will give you is the total number of electrons that were processed in the equation. And if you carry this out, you find out that that's equal to 6.022 times 10 to the 23rd. And the idea is that because you were dealing with copper 1, automatically the charges of the electrons cancel out exactly with the coppers. So if you do have 6.022 times 10 to the 23rd electrons, you have to have 6.022 times 10 to the 23rd atoms of copper, which ultimately turned into 63.55 grams of copper. So technically speaking, Avogadro's number is the means by which we can switch over from ultimately the number of atoms or molecules or ions that we have present into the mass that we see in the periodic table. Now, the more direct thing in regards to Avogadro's number is called the mole. 1 mole of a substance, which is the bulk sample, is equal to 6.022 times 10 to the 23rd atoms, molecules, or ions. And we also abbreviate Avogadro's number with N subscript capital A, not to be confused with sodium. That's different, right? That will be capital N lowercase a. This is not lowercase a. It's a subscript and it's uppercase. All right, but Avogadro's number will allow us to carry out the conversions to go from atoms to moles. And once we have the moles, we can find out what the mass of the substance is. So let's take a look at the conversions. All right, so as you saw in the previous slide, you can go from moles to atoms, or you can go from atoms to moles using Avogadro's number as your conversion factor. You could also go to molecules if that's what you're dealing with, using Avogadro's number. You could go to formula units using Avogadro's number. So depending on what you have, if it's an atom of just the element, or if it's a molecule, or if it is an ionic substance, you're going to have the different denomination. But all in all, you will have to use Avogadro's number to go from moles to any of those three, or to go from any of those three denominations into moles. And to go from moles to grams, we're going to use something known as the atomic mass, which is the number that we see in the periodic table. And lastly, by now you do know that for a pure substance, if you have the mass of the substance along with the density, you can find out the volume of the substance, and vice versa. If you have the volume of the substance with this density, you can find the mass. So this whole roadmap tells you how to go from one thing to another, with everything in red here on top of the arrows representing the conversion factors themselves. All right, so let's do a few examples to see how this plays out. We want to find out the mass in grams of FeCO5 present when you have 9.48 times 10 to the 22nd molecules of that component. So the first thing we do is we acknowledge the fact that we are looking for grams and we're starting with molecules. So we're going to write down the value, 9.48 times 10 to the 22nd molecules, and we look at the roadmap. For molecules, the only place we can go is into moles. In order to enact that transformation, we have to use Avogadro's number. And because we have molecules on top, right, that's the initial number we start with, we have to place molecules on the bottom. And wherever the molecules, atoms, or ions go in terms of units, that's where you want to place Avogadro's number. All right, and the opposite end of the fraction, you'll have 1 mole. So in other words, 1 mole of this substance equals 6.022 times 10 to the 23 molecules of the substance. All right, so the molecules cancel out. Now, what we need to do is to go from moles to grams. And the way we do this is by using the atomic masses of the elements. And specifically, notice that we have 1 iron, and the 5 that is outside in parentheses, or outside of the parentheses, means that the 5 applies to both the carbon and the oxygen. So this is more in line with Fe, 5 Cs, and 5 Os. And so what we're going to do now is we're going to look at the periodic table. And we're going to use the atomic masses that we find in the periodic table along with the proportions that we see in the formula to come up with the overall mass that this molecule has. So let's take a look at the table. Iron has an atomic mass of 55.85 grams per mole. Okay, so the units are grams per mole. Carbon has an atomic mass of 12.01 grams per mole. Oxygen has an atomic mass of 15.99 grams per mole. And so, coming back at the problem, we have 1 iron, so we multiply the 1 iron by the 55.85 grams per mole. We have 5 carbon, so we multiply the 12.01 grams per mole by 5. And for oxygen, we multiply the 15.99 grams per mole by 5. And so we carry out the multiplications in each case. And at the very end, all you do is you add up all the values together. The resulting value you get here is the molecular mass or molar mass. And this tells you the overall mass that you will have for that entire compound if you have 1 mole of the compound. Now this is the conversion factor we're going to use to go from moles to grams ultimately. So going back to the problem, since we have moles on top, in the next fraction we're going to have moles in the bottom. And the molar mass, 195.85 grams, will have to go on top. Alright, so at this point you have to carry out the calculation. And what I recommend that you do is that for the exponential numbers, use parentheses in your calculator. So open parentheses, enter 9.48 times 10 to the 22nd, close parentheses, divided by, open parentheses, 6.022 times 10 to the 23rd, close parentheses, press enter. Multiply to your answer 195.85 grams and press enter. You should end up with 30.8 grams. It is vital and crucial that you do use parentheses for the exponential numbers because your calculator may misinterpret what you're trying to do if you don't use the parentheses. All right, let's do a few more problems. Here we're going to find out how many grams of manganese 2 chloride are present if we have 2.47 times 10 to the 19 manganese 2 chloride formula units. This is the same thing as molecules, except it's now applied to ionic substances. All right, so we start once again with the formula units. And based on the roadmap from the formula units, the only place we can go is to moles, and we need Avogadro's number to carry the transformation. So formula units are on top. We'll make sure to place formula units on the bottom. Avogadro's number goes along with the formula units. The 1 mole goes on the opposite end of the fraction. All right, cancel out formula units. Now we're going to look at the molar mass of manganese 2 chloride. All right, so we need to look at the periodic table. Manganese has an atomic mass of 54.94. Chlorine has an atomic mass of 35.45. So we multiply the 54.94 grams per mole by the 1 manganese that we have present. and we multiply the 35.45 grams per mole of chlorine by the 2 chlorines present. All right, so we get the following values, and now you add them together to get 125.84 as your molecular mass. All right, so now that we have that value, and because we have the value as grams per mole, the 125.84 grams have to go together. The mole goes separately in terms of writing the fraction. You have moles on top in the first fraction, so you make sure to place the moles on the bottom on the next fraction. And then the mass itself goes on the opposite end of the fraction. The moles will cancel out, now you have grams. And like before, you do have two exponential numbers, so open parentheses, enter 2.47 times 10 to the 19, close parentheses, divide by, open parentheses, 6.022 times 10 to the 23rd, close parentheses, press enter. Then multiply your answer by 125.84 and press enter, and you should find out that the mass is 5.16 times 10 to the negative 3 grams. You could also say 5.16 milligrams if that's an option that is allowed in the problem. All right, let's move on to another example. Now here I want to find out the number of hydrogen atoms present in 2.3 grams of this molecule. Okay, so here there are going to be a few things that happen. First of all, the initial value is at 2.34 grams of the molecule. So what we need to do now is, since we have grams of the molecule, there's multiple places we could go. But the only place that's going to take us towards number of atoms is to go towards moles. So we're going to convert the mass to moles, and we're going to have to use the molar mass of the compound. So let's take a look at that C3H6Br2. Looking at the periodic table, hydrogen has an atomic mass of 1.008, carbon 12.01, and bromine 79.90 grams per mole. So we're going to use each of those masses, and just make sure to multiply the atomic masses by the proportions in the molecule. So carbon is multiplied by 3, hydrogen is multiplied by 6, and bromine is multiplied by 2. If you multiply each one of those values and then add them together, you now find out your molar mass, which is 201.9 grams per mole. Okay, so coming back to this problem, we start with 2.3 grams of the molecule. We divide it by grams of the molecule. We know the value to be 201.88 from the previous calculation. In the opposite end of the fraction, we have 1 mole. So the grams cancel out. Now you have moles. All right, so here is where you have to be a little bit careful, because ultimately you're looking for the number of hydrogen atoms. This is not the moles of hydrogen. This is the moles of the molecule. So here you have to ask yourself the question, well, in 1 mole of this molecule, how many moles of hydrogen do you have? And that's the same thing as asking, in 1 molecule of C3H6Br2, how many atoms of hydrogen do you have? And as you can see here, there's 6 atoms of hydrogen. So in 1 mole of that molecule, you ought to have 6 moles of hydrogen, and that becomes your new conversion factor. This allows you to go from the molecule in terms of moles to the number of atoms, in this case the atoms of hydrogen in terms of moles. Once you have the proper moles, now you can use Avogadro's number. Now you can go from moles of hydrogen to the atoms of hydrogen. And since you have moles on top, you have to make sure to place moles on the bottom. And on the very top of the fraction, you will have Avogadro's number. So now what you need to do is carry on the calculation. So in your calculator, what you will do is enter 2.34 divided by 201.88, press enter. Then multiply by 6, press enter. Then multiply by 6.022 times 10 to the 23rd, press enter. And just to keep everything consistent, you might want to actually use parentheses around the Avogadro's number value. But if you do this correctly, you should end up with 4.19 times 10 to the 22nd hydrogen atoms. All right, one more. We're going to find out how many molecules of C2H5OH are present in 5.43 milliliters of this substance, with the information being given that the density of the substance is 0.79 grams per ml. Alright, so we start with the 5.43 mLs, and looking at the roadmap, with volume, the only place we can really go is the mass. And we need to use the density to make that conversion. So if we have 5.43 mLs of C2H5OH, we have to have mLs on the bottom and grams on the opposite end. Now, because the 0.79 is in front of grams directly, the 0.79 goes with grams. The mLs will have to have 1 as its placeholder value. Alright, so this allows you to be in grams. Now we have to switch to moles. And in order to do that, we need to find out the molar mass of this substance. So once again, look at the periodic table: 1.008 for hydrogen, 12.01 for carbon, 15.99 for oxygen. Multiply each one of those values by the corresponding amount. We have 2 carbons and we have 6 hydrogens. So be careful here. You actually have 6 hydrogens altogether, not just 5. And 1 oxygen. So multiply each one of the values together and add them up together to yield the molecular mass of the substance, which is 46.06 grams per mole. Alright, so we have the mass on top. Now we're going to place the mass on the bottom, 46.06 grams. The 1 mole will go on the opposite end of the fraction. And right now, all that you have to do is switch over to molecules, right? So we're going to go from moles to molecules. So we need to use Avogadro's number. Since we have moles on top, you have to have the 1 mole on the bottom, and Avogadro's number will go on the opposite end of the fraction in terms of molecules. So to finish the problem up, all you have to do is multiply 5.43 by 0.79, press enter, divided by 46.06, press enter, and then multiply by 6.022 times 10 to the 23rd, press enter, to find out the value to be 5.61 times 10 to the 22nd molecules. Alright, so this gives you the whole idea of conversions. We've gone through 4 really robust examples, so hopefully this gives you the picture of how to go about performing the conversions. In the next video, we're going to start talking about mass percent and empirical formulas.